In my work, I research on CO2 Laser micromachining of coated polymethyl methacrylate for microfluidic applications. Over the past few years, there has been a growing interest in the use of microfluidic devices. They are used in applications like in the medical field, in the chemical field, electronics, and many other applications. The devices use microchannels in applications like DNA analysis, chromatography, and electrophoresis, among others. Now, why are the microfluidic devices highly demanded? Initially, they were made using quartz, silicon, and glass. But currently, they are being made using PMMA. So that the devices are highly demanded because of many reasons. Number one, they use small amounts of reagents and samples. They also reduce the cost of reagents, and they have short analysis time. And the cost of fabrication is low. And also, they have high sensitivity, repeatability, portability, and biocompatibility. Why are polymers like PMMA being used to make the devices instead of silicon, glass, and quartz? Many reasons. Polymers like PMMA have several properties like lower cost of fabrication, good optical transparency, biocompatible, and they're also cheap and they're disposable. And most importantly, they have high absorptivity of about 95 in the infrared region. And then CO2 laser version of PMMA is cheap, simple, flexible, and time effective. But the process makes it very difficult to achieve precise dimensional control because the values of the properties of the material change under different conditions. And then also thermal defects result. So the thermal defects include melting of the PMMA, clogging, heat affected zone, high surface roughness, and desolidification, among others. What are the solutions? The solutions are to coat the material before fabricating the microchannel with the material. The second solution is to control the inputs like power, speed, and pulse rate. Now, the main objective of this work was to improve the quality of the microchannels fabricated on coated PMMA using CO2 laser. How did we achieve this? Two specific objectives. Number one, to investigate the effects of power, speed, pulse rate, and coating the PMMA substrate with 99.95% pure aluminum on the quality of the microchannels. Number two, to determine the optimum set of inputs, power, speed, and pulse rate for CO2 laser micromachining of aluminum-coated PMMA using response surface methodology. And the last one, to model CO2 laser fabrication of microchannels on aluminum-coated PMMA using adaptive reinforcing inference systems. Now, what did we do and what did we not do? We studied the effects of power, speed, and pulse rate on microchannel width, depth, aspect ratio, surface roughness, and heat affected zone. We also carried out optimization and statistical analysis using response surface methodology. Finally, we did artificial intelligence modeling using adaptive reinforcing inference system. Now, we looked at the work of some people who have gone before me, and we realized that Chung and others did wonderful work. They coated the material with 0.03 millimeter thick metal film made by wet etching using SUS 304 stainless steel in a solution of iron free chloride. And then they fixed power at 1.5 watts and speed at 34.2 millimeters per second, and they fabricated holes in air and with a metal film. This is what they got in air, the first one, and this is what they got in the metal film. And they found out that the bulge height was 10.6 micrometer in air, and it reduced to 0.4 micrometer with the film. The whole diameter was 305 micrometer in air. It reduced to 103 micrometer with the film. And then Mohammed and others carried out a very interesting study in 2015. They used speed from 5 to 12.5 millimeters per second, and the power from 2.4 to 6 watts, and pass rate was fixed at 1000, the maximum. And they coated the material with 300 micrometer layer of water, and they fabricated in both air and in water. This is what they got in air, and this is what they got underwater. At 3.6 watts, 5 millimeters per second, and of course with the coating fixed at 300 micrometer of water. And then they were able to reduce heat affected zone from 493 micrometer at 5 millimeters per second in air to 142 micrometer at 12.5 millimeters per second in water. Pretty good work. This is in air, this is in water. And then in another study, Mohammed and others again carried out a multi-objective optimization using the Gucci method of design experiment. Power was 3, 3.6, and 4.2 watts, and the speed was 15, 20, and 25 millimeters per second, and the pulse rate was 800, 900, and 1000 pulses per inch. And then this is the plot of surface roughness that they produced. They also performed analysis of variance to determine the significance of the inputs, power, speed, and pulse rate. And they found the optimal conditions in both air and water to be 3 watts, 20 millimeters per second, and 900 pulses per inch. This is what they got. The one they got at higher speed is better. Now, we also looked at the work done on artificial intelligence modeling of CO2 laser micromachining. With fuzzy logic, Hussein and others modeled the curved width in CO2 laser ablation of PMMA. This is what they did. And the inputs were assist gas pressure, power, speed, and standard distance. And they were able to get a relative error of 3.852% and goodness of fit of 0.994, which indicates high accuracy of their work. And then Aluminium and others used response surface methodology, adapted neural fuzzy inference system, and artificial neural networks to study curve taper and material removal rates in laser beam machining and laser welding of aluminum oxide metal matrix composite. And this is what they plotted for the 3 methods. They found that ANFIS has the best prediction accuracy in both processes. ANFIS is the method we use in our work. Now the experimental work, what did we do in the lab? The work was divided into 3 parts. In the first part, we looked at the fabrication of microchannels of aluminum-coated PMMA using a low-power CO2 laser. These are the values of the inputs. We vary power from 1.5 to 7.5 watts, and the speed from 5 to 17.5 millimeters per second. And we fixed the pulse rate at 1000 pulses per inch. We coated with 1 micrometer layer of aluminum. The work material was a transparent PMMA measuring 30 millimeters by 25 millimeters by 6 millimeters. Using the laser machine, we cut the work samples from a large sheet of PMMA. And then using the deposition machine, we deposited the layer of aluminum on top of the samples. And then using the CO2 laser, we fabricated microchannels. And then using an aluminum etchant, we remove the aluminum coating. And then we use the 3D laser microscope to characterize the microchannels. In part 2, we examine the process using response surface methodology as a technique of design experiment. We use Minitab 19.1 to design experiment, and we use 3-level central composite design. We conducted 18 experiments, which we repeated 3 times to get 54. Of the 18, 8 were the factorial points, and 6 were the actual points, and 4 were the center points. Totally 18, and then we multiplied by 3, so we did 54 experiments in total. This table shows the design in Minitab. We varied speed from 10 to 20. We used 10, 15, and 20. Power was 1.5, 3, and 4.5. and the pass rate was 800, 900, and 1000. We did analysis of variance to determine the significance of the parameters, and then we were able to optimize the parameters. And then the third part, we modeled the process using adaptive universal infinite system. Adaptive universal infinite system combines fuzzy logic and AMN. In our work, we use three membership functions, and we chose the Gaussian type, membership function type, and then we use the following equations to fuzzify the inputs. And then we use the following equations to fuzzify the responses. These equations, they have the same meaning. For example, for power, it means we vary power from 1.5 to 4.5. So for surface roughness, it means the minimum value we got was 7.134 micrometer, and the maximum was 42.518 micrometer. Then, how did we do that? First, we used the Amphis toolbox in MATLAB 2022A. Why? Because it was the latest version at that time. And then we used the 54 experimental values for the response surface methodology. We divided the data into two parts. The first part, 70% was used for training, and 30% was used for checking. And then we loaded the data with all the inputs, but only one output. Because Amphis accepts only one output at a time, we were able to then produce the system. We set the error tolerance to 0, and we trained the system. We obtained 27 rules automatically using the training data. And then we produced the surface plots. And finally, we analyzed the results using Minitab 19.1. Then we assessed the models using the following equation. We got absolute prediction error with this equation, and then we got the percentage error with this equation, and then we got the relative error with this equation, and we got the goodness of fit with this equation. So the results and discussions. What did we get out of the work? In part 1, we were assessing if the coating has any effect on the quality of the microchannel. So we used the pass rate as 1000, and the power from 1.5 to 7.5, and the speed from 5 to 17.5. We were able to get better microchannels on the coated samples compared to the uncoated. This is what we got. Figure A is what we got when we did not coat, and figure B is when we coated at 1.5 watts and 17.5 millimeters per second. The one we got with the coating is surely better than the one we got without the coating. These are the 3D images we got at the same condition, 1.5 watts and 17.5 millimeters per second. The first one is uncoated. The second one is coated. We examined the effects of the inputs on the outputs. We plotted the graph of the microchannel width against the laser power. And then we plotted the graph of the width against the scanning speed. And we found that microchannel width increases with the increase in power. At 7.5 watts and 5 millimeters per second, for the uncoated we got 739.005 micrometers. This value reduced to 335.215 when we coated. For the microchannel width against the speed, for the uncoated we got 322.435 micrometers. It reduced to 129.998 micrometers. We did the same thing for the depth. The depth reduced from 998.396 to 780.325 when we coated at 7.5 watts and 5 millimeters per second. And then at the minimum power and maximum speed, when we did not coat, we got 168.158 micrometers, and the value reduced to 93.066 when we coated. For the aspect ratio, now we got the aspect ratio by dividing the depth by the width. And then we plotted the graph of aspect ratio against the power. At the maximum power and the minimum speed, we got aspect ratio to be 2.633 for the coated. And then for the uncoated, it was 1.415. So we can see that coating increases aspect ratio. And then at the minimum power and maximum speed, for the coated, aspect ratio was 0.716. And for the uncoated, it was 0.522. High aspect ratios are used in applications that require high fluid flow, like cell screening. But there are also other applications that need low aspect ratio, like DNA examination and particle separation. And then we did the same thing for surface roughness. We plotted the graph for surface roughness, again it's a laser power. Surface roughness increases with the increase in laser power. So at the maximum power and the minimum speed, for the uncoated, surface roughness was 310.254 micrometer. And for the coated, the value reduced to 84.692 micrometer. When we plotted surface roughness with the scanning speed, at the minimum power and the maximum speed, for the uncoated we got 25.579 micrometer, and when we coated we got 9.020, and this was the smallest value we got. The same thing for heat affected zone. At the maximum power, minimum speed, uncoated 486.225, for the coated 328.874. And then part 2. In part 2, we use response surface methodology as a technique of design experiments. We use power as 1.5, 3, and 4.5 watts, and the speed 10, 20, and 30 millimeters per second. And the pulse rate 800, 900, and 1000 pulses per inch. Now this is a laboratory profile we got at 4.5 watts, 15 millimeters per second, and 900 pulses per inch. The profile is affected by many factors. Number one, the nature of the work material, the laser speed, and the number of the laser passes, pulse frequency, power, and other factors. We performed analysis of variance to determine the significance of the inputs on the responses. This is what we got. X denote factors that are not significant. For example, for the width, the square of the pulse rate was not significant on the volume of the width. So we did the same thing for all the responses. Then we examined the interaction effects of the inputs on the responses using response surface methodology. And we were able to plot the following graphs. Now all these figures communicate the same thing. The same thing. The first one, now the channel width against power. It shows that width increases with the increase in power, but decreases with the increase in speed and pulse rate. Now these figures show the same thing. For the channel depth, we plotted the graphs as well, and all these figures show the same thing. We can see that the channel depth increases with the increase in power, but decreases with the increase in speed and pulse rate. All the figures show the same thing. We did the same thing for the aspect ratio. And we can see that aspect ratio increases with the increase in power, but decreases with the decrease in speed and the pulse rate. Then the same thing for heat affected zone. It increases with the increase in power, but decreases with the increase in speed and pulse rate. The same thing for surface roughness. All the figures show the same thing. Now this one shows the interaction effect. How the interaction of the inputs affect the values of the output, which in this case is surface roughness. So we did mathematical modeling of the responses using response surface methodology. And we were able to get equations that can be used to approximate the values of the responses. The first one is for the width, the second one is for the depth, aspect ratio, heat affected zone, and surface roughness. And this is the nomenclature of the letters. And then we compared the experimental results with the predicted results using response surface methodology. And we got the following figures. The red lines represent the predicted values, and the black lines represent the experimental values. As we can see from all the figures, for all the responses, the values are very close. This indicates high accuracy of the work. with response surface methodology. And then we did multi-objective optimization of the parameters. The goal was to minimize width, to minimize state affected zone, to maximize aspect ratio, to maximize depth, and then of course to minimize surface roughness. We found the optimum values to be 3.2273 watts per power, 12.0202 millimeters per second for speed, and then 1,000 pulses per inch for the pulse rate. And then we validated the results using 3 experiments at the optimum value. And then we got the mean values of the responses, and then we compared with the predicted results. We calculated the absolute percentage error using this equation, and this is what we got. The maximum value is 3.12% for surface roughness. And then we did repeatability tests to determine the repeatability of the responses. We conducted 10 experiments at the optimum value of the inputs, and then these are the results we got. As we can see, the values are very close. And then we were able to plot these figures to show the repeatability of the responses. The dotted line represents the mean values. In the last part, where we use adaptive universal infinite system to model the process, for the Parmesan width, these are the rules that we generated from the rule editor in MATLAB, and then these are the rules from the rule viewer. Now from this rule viewer, if you know the values of the inputs, you can enter the values and be able to get the values of the width. For example, for this particular case, power is 3 watts, speed 15, and the pulse rate is 900 pulses per inch. And it gives the value of the width as 135 micrometer. This is the structure of the unfixed model for the width, and then this is the training error. It did not exceed 1.1. This is the training data. We divided the data into the two parts. 70% was used for training. This is the comparison of the actual values, experimental values, and the predicted values of the training data. And this is a comparison of the checking data, actual values and the predicted values. We plotted the Parmesan width against other experiments to compare the experimental values and the predicted values. As we can see here again, like we saw for the case of the response surface methodology, the experimental values are close to the predicted values. And then we plotted the predicted values against experimental values to get the line of best fit. And all the values fall along that line. And then we produce the surface plots. And then we did the same thing for depth. These are the rules. This is the structure of the unfixed model for depth, the training error, the comparison of the training data, the actual values and the predicted values, and the comparison of the checking data, the actual values and the predicted values for depth. We plotted the depth against the random of experiments to compare the experimental values and the predicted values. And then to get the line of best fit, we plotted the predicted values against the experimental values. Again, all the values fall within the line of best fit. These are the surface plots we got. We did the same thing for aspect ratio. The rules, structure of the unfixed model, and the training error, and the comparison of the training data, the 70%, the actual values, and the predicted values. And then this is a comparison of the actual values of the checking data with the predicted values. We put the aspect ratio against the random of experiments to compare the experimental values and the predicted values. Again, we can see they are close. And we plotted the predicted values against the experimental values to get the line of best fit again, like we did for the other responses. Again, we can see that all the values fall within that line of best fit. We did the same things for heat affected zone. And we did the same thing for surface roughness. The rules, unfixed model, training error, training data compared, actual values and predicted values, and the checking data compared. And again, we plotted the surface roughness against a number of experiments to compare the predicted values and the experimental values. And then we got the random best fit, and we got the surface plots, the surface roughness. What can we conclude from this work? Number one, we found better number channels on the coated samples than on the uncoated samples. And then we got smaller values of width, depth, surface roughness, and heat affected zone, but higher values of aspect ratio when we coated. And then we found that width, depth, and heat affected zone and surface roughness increase with the increase in power and decrease in both speed and pulse rate. And then the aspect ratio increases with the increase in power and the decrease in speed and pulse rate. When we optimize with response surface methodology, we found that power is the most significant factor, followed by the speed and the pulse rate. We also found that the interactions among the inputs affect the responses, as we saw. The models we developed with the response surface methodology have high accuracy, as we saw from the lines of best fit. And we found that the larger the number of experiments, the better the accuracy. We also found that low power with high speed and pulse rate lead to good results, lead to low thermodynamics. And then the unfit models we developed have high prediction accuracy, and they can be applied in examining other models for CO2 laser micromachining of our material. The ultimate conclusion is that coating PMMA with 99.95% aluminium improves the quality of the microchannels fabricated on the PMMA substrate. This is the main goal of the work. So we did not do everything. That means a lot still has to be done. So what should be done? Number one, future studies should consider other inputs like standard distance, pulse width, and air pressure, which we did not consider. Future studies should also consider other responses that we did not consider, like the bar width, dimensional deviation, and the bar height. Future studies should also consider other shapes of the microchannels, like trapezoidal, snake shape, and circular shapes, which we did not consider. In our work, we considered only rectangular shapes. Other materials should also be fabricated, like ceramics, composites, metals, and other polymers, like PC, PET, and PDMS. Other coating materials should also be used, like chromium, silver, and Borg, and their effects should be examined. Future studies should consider fabricating microchannels using varying laser passes. In our work, we use only one laser pass. 3D finite element modeling and simulation should be done in future studies. And higher values of power, speed, and lower values of pulse rate should be considered in future studies. We got some publications from this work. And then here's a very interesting statistic that I got. The global microfluidics market size reached about $20.9 billion in 2021, and it is projected to reach $52.4 billion by 2027. This is according to the International Market Analysis Institute from Fath in 2022. This shows the high potential of this field. Ultimately, more research will still be done in this field because it has high market value. So, I thank the following people and institutions for their support. First, Aegis. And then I thank Chicat 7 for the scholarship, and JICA, and STDF that funded the lab in which I work, and then the government of Japan, and the government of Egypt. And I thank all my colleagues for attending and for being with me throughout the journey. And of course, my professors, Professor Hassan El-Hofy, from my advisor to supervisor to now examiner, and Professor El-Bab, from day one, when we start to plan the work, up to now, we are together. And when I met Professor Samy Ebeid at his home, we had a very interesting discussion about the work. And I was impressed by his humility when he received me and my colleague and we sat and discussed. Now, when I went to see Professor Mahmoud Shaban to deliver the thesis, I did not call him when I was going. I called him when I was about to reach, but he was so understanding. And he sent a professor to go and collect the work when he was already out of the university. So thank you so much, professors. Thank you, everybody. God bless you. This is the work what I did.
Thank you, Job, for your well-ordained presentation. And I also thank the supervisors, Professor Hassan and Professor El-Bab. I would like to start. I have really many questions to ask. First of all, it was very strange for me to see a thesis with one big error. There are no numbers for the pages. I have discussed tens of theses, whether MSc or PhD. This is the first time for me to see such a thesis. Do you agree?
Yes, I noticed it.
Without numbers,
I noticed it.
without page numbers. So when I ask now, how shall you follow me? It's very strange, really. Okay. Well, I have a lot of questions. First of all, if you open the table of contents, the numbering starts with 2 Roman, 3, 4, okay? And then after number 8, we find number 5.
After number 8?
Yes, it's written number 5, page 5, page 5, page 10. In the table of contents.
Oh, I don't have it in my Bible.
Well, I am asking about the thesis you gave me. Do you have it? Okay. Table of contents. You see, the numbers is not correct. So this should be corrected. And then, if we jump up to list of tables. The list of tables. You start with table 4.1. Is it correct?
Yeah, 4.1.
Then 6.1. Where are 4.2 and 4.3 and 4.4? They are listed in page 48. If you open page 48, so table 4.1 should come after 4.1, 4.2, 4.3 and 4.4. They are listed in page 48. Okay. And then in the list of figures, can you get the list of figures? It's a wrong page written. List of figures, yes. Get figure, go down to figure 3.3. Okay? 3.1, 3.2, 3.3. After 3.3, you write figure it's written 6.1. Where are figure 4.7 stated in page 58? In 58, you refer to figure 4.7. It's not written. It's not written in the list. Okay? And then go down again, 6.3 up to 6.7, and then suddenly 6.9. Where is 6.8? It's in page 47. And then starting from figure 6.9 up to the end of the thesis, they are all wrong. Okay? They are wrongly numbered. كله غلط. كل الفيجرز غلط. حضرتك تقرا هنا والارقام غلط. And the last figure 642. Can you show me figure 642 in the thesis? It isn't found. Don't search, it isn't found. Figure 642 is not found in the thesis. Where? Which page?
Page 102.
The last figure I have it, 641. I don't have 642 in the thesis. Fish. The copy you gave me doesn't include 642. Then if you open page 4, page 4, section 1.5. Section 1.5. The thesis consists of 6 chapters. So you give me another copy. And this is not correct. I have it written 6 chapters. No 6. It's written here 6. So أنا كاتب له. And then in page 28, page 28, in the middle of the page, in the second paragraph, by page 28, by sputtering 12 samples, page 28. But 28, by sputtering.
Second paragraph, page 28.
Yes, here. By sputtering, it's written 12 samples, correct? And if we open page 31, it's written 18 samples. Page 31, third line from down. Section 422. 18, second line, 18 specimens. Third line from down. How can this come? Which is correct?
No, this one was for the response surface methodology. Because on each sample we fabricated 3, so 3 times 18 is 54.
Well, what are the 12?
Was for the first part, for part 1. They were 12.
But you didn't, yani, nothing shows this.
4.2 is part 2. 3.2 is part 1. So the numbers are different in the different parts.
But you should have included this, yani. And the same also for the coating. In page 28, it's 1 micron. In page 32, it's half a micron. But it's not clear here, yani. So please clarify this point. And then if we go to chapter 4, and chapter 3, I think they could have been combined together. Chapter 3 is around 3 pages. Chapter 3 is around 3 pages. Why a separate chapter?
Because they represent different parts.
But they are under experimental work. They could have been combined together.
I can combine them.
Experimental work. For you state in chapter 3 experimental, and then in chapter 4 experimental again. Also in chapter 32, chapter 32, just above 4.3.
Chapter 32?
Page 32. Just above this chapter, above 4.3. You are speaking for the aspect ratio. Yes, only. You speak about the aspect ratio. I think it should be better to put a sketch here to explain what is the aspect ratio. Okay? To define this and to show the conical shape. And then in page 33, and all over the thesis you write equation number so and so. I think no need to write the word EQ. No need to write it at all. And then in page 33 also, page 33,
Section.
431. Yes, yes, down please. Yes, here. After equation 4.1, you start a sentence with K. I think it's not correct to start with a small letter with a symbol. And then you repeat it again after 4 lines with epsilon. So from the English point of view, I think it's not suitable. And in page 36, section 5.2, in 5.2, second line, built on Tagaki Sugunu Fuzzy. Where is the reference?
49.
Where?
49.
You should write it beside the name, not at the end of after 6 lines or. In section 5.3, you are giving 4 equations. Is epsilon equal to PE over 100? Epsilon. Is it PE over 100?
This one. This one.
Yes, epsilon. Is it PE? PE over 100? Its value? This is found in page 63.
And that's section.
Page 63. You have table 6.8. The values of epsilon are the values of PE over 100. You list a lot of numbers. Is it correct what I understand? صح كده?
This is the equation we use to get the.
Yes, its value is the same value as PE over 100.
I didn't notice that in the computation.
This is what is shown in the tables. And then in page 40 in section 612. Okay? It's written, yes, in the 3rd line from down, it's written the heat input is high. Did you see it? The heat input, section 612, above the curves, from down, go down. Okay. The heat input is high, and the line after it the heat input is low. You saw these two words, high and low?
It is low at low power and high speed.
I think from the engineering point of view, we can't say high and low. You should put figures. What do you mean by high? This is high, this is high, this is high. Try to put a figure. And this also is found in page 41, the same words. High and on page 42 and so on. And then in page 43, the second line from up.
What is the section?
Section 612. Yes, go down till part D, surface roughness. Before, yes, surface roughness, please. Yes, surface roughness. Go down, down, until the second page. Yes, the second line from up. The percentage decrease in the microchannel depths. It's not the depths. You are speaking about surface roughness. So it's wrong. You saw it? Then if we go to section 621, the microchannel profile. Yes, go down please. The paragraph starting with the shape, yes, the shape. From the shape, the third line, the fourth line, you write 3 watt, 15 millimeter per second, and 900 ppi, correct? If we go to the figure, it's just below it. It's not the same. It is not 3 watt, it's 4.5 watt. And you are referring to this figure. You realize this?
Yes.
They are not the same. And of course, as I have said before, all the number of figures are wrong. And then when, if you go to section 622, yes, ANOVA helps. You state here table 4.2 and 4.3. They are not found in the thesis. In the list of figures, in the list of tables, they are not written, and there are no tables with these numbers. What is 4.2 and 4.3?
This process is done, but we put some mark on the title and make it fresh and compute. So sorry, this is the
No.
fourth error of frame and error of definition.
No, but it's an error. There are no tables in the text numbered 4.2 and 4.3. What do they include? I don't know. They are not found.
Suppose it is
Suppose what? 6.2.
4.2 and 4.3 now.
And yes, where are they?
No, that's another one.
لا بس حضرتك مش موجود. مفيش تيبل اسمه 4.2. Also in the page after it, table 4.4, where is it? Not found in the thesis. And then from page 51 up to 56, the curves are very small. Why? Section 623. Are you saving paper or? Are you saving paper?
No. We can elect this.
Very, very small figures. How can I read this? Okay. These are from 51 to 56. In page 54, you see it's part D. Part D, heat affected zone.
Section.
Section. Yeah, section. 623. Part D, heat affected zone. Part D, yes. Part D, at the end of the paragraph, there is a figure 0.004%. Okay? If you go to the table 6.3 in page 50, there is no such figure. From where did you get it? In page 50.
Section.
Page 50. That's before it. Table 6.3. But then it says here, scan speed and pulse rate. Scan speed, pulse rate. Where is it? Yes, this is, where is 0.004%?
No, this is the summary for all the responses. That one is from the specific table for heat affected zone.
No, it's written the scanning speed and pulse rate. It's written, it's for this. It's not found.
In this table, we left out the points that were not significant in this table. The values that were not significant, we did not include in the table.
Yes, but from where is this figure? From where did you get it?
The table.
The number. How do you calculate the number from the table?
The numbers came automatically from the design in Minitab.
But you refer to the table 6.3. So I should find it in 6.3. And there is also another figure. Above it by 2 line, 0.018%. It's not found here.
Job, you have to write how did you get this number from the table, okay?
Okay.
Yeah.
And then after this, in page 58, 625. Okay, starting from page 58, okay, the units are not found. For example, the table, you write power. What is the unit? Speed, no units. And this is also from page 66 up to page 83, there are no units. This could not be accepted. All figures, no units. And then in section 6 to 8, process accuracy examination. Okay? The first line down of the input starts of the inputs obtained from the multi-objective optimization. 3.227271. How did we get this number?
This one came automatically from the software. It's not automatically.
Up to 5 decimals?
It gives even more than this, depending on the setting.
Measurables?
Hmm?
Is this number measurable?
No, this number is given by the software based on the values of the inputs that we put.
Okay. In section 631, yes, this one. If you go to, we'll speak the columns from the left, from the right, okay? The one, not epsilon, APE, which starts with 0.926. This is not the value of APE. It's the value of PE. And the title, its title is absolute percentage error. It's wrong. And the column to the left of it is APE. I think, Job, you didn't revise it correctly. And then go down, please, after the table. Yes, more. Yes, the figure on the right. What can I understand from this figure?
The figure on the right is shows the rules generated from the whole.
Yes, but what do I see from here, in the paper here? What do I see in my paper? Nothing.
Or it is small.
It's very, very smooth. And then I go to page conclusions. There is something which is not correct in the conclusions. The conclusions is given in around three pages. It's very long. Secondly, the contents of the conclusion You have to understand what should be written in the conclusion. You are explaining some facts, they are not conclusions. And if I were you to write the conclusions, it would have taken half a page. For example, in the second paragraph, the main objective of this study was to, this is not a conclusion. The same applies to recommendations. Same applies to the recommendations. For example, in part A, you state in part A, the study was limited to only part. Well, you said this before. Why are you repeating it? The recommendation here should start from the third line. The study should be extended to that. Well, these are also some sentences in English are not correctly written, okay? And some parts you state, I have to search for the number. Yes. For example, if we go to page 41, I don't know where the section, it's section, it's section part C, aspect ratio, above aspect ratio, section 612. Above figure 6.4, above 6.4. Yes, the line just above 6.4. This decreases the microchannel depth 2739. Correct? What does this mean? Do you agree with the reference or you disagree with the reference? This is stated maybe 3 times in page 41, 44, and 59. Do you agree or you disagree?
It is true that low power and high speed decreases the
I can't understand. You say this decreases. But did the reference say the same thing? Or the reference said against what you are saying?
You said the same thing.
So how can I know? You should state. This is also according to reference kaza kaza. You didn't also, this I think it will not be done by you, the Arabic, there are many errors in Arabic, in the Arabic page, in the title and in the summary. It's full of mistakes from Arabic. You don't know Arabic? Okay. So please revise. It's not nice to have it like this. Did you show in the thesis any practical applications for microfluidic channels?
Applications?
Yes.
In the introduction.
You just stated in introduction, but you didn't give us an application.
Okay,
I'm looking for an application.
Microfluidics is very well known now, usually in medical analysis, and they can use it in cell separation and chemical mixing and so on. So I think the application, the general application, is very well known, and the challenge is how to fabricate microchannel in low cost and high performance.
agree with you, Professor, but he should have shown some applications.
I will show.
Okay? And then, why you didn't use ND-YAG laser? Is there a reason?
We don't have it here.
Just for not having it.
We have only CO2 laser. The only available is here.
ND-YAG. 1/10 of the CO2. 1.06. You didn't state why. It's just only you don't have the width.
No. Also, I guess from the absorption point of view, this wavelength absorb well this plastic. The other one has some limitation.
But it didn't state
This is the
anything.
best for acrylic, by the way. Very big absorption.
And how did you get the 99.99% aluminium? Or 99.95?
It is spotted. It is spotted on the top.
Thermal evaporation. The wire.
The aluminum wire.
The wire negative.
But you didn't check it.
We didn't test it.
يعني على الورق لا.
Okay. I am about to finish. Sorry for all this. In page 28, in section section 3. You said that you added a lens at the beginning. You added a lens, okay? 130 micrometer mean spot diameter. Did you get this part? What do you mean by you added a lens? How did you add a lens to the machine?
The lenses can be changed.
Actually,
The lens can be changed.
machine has this very advanced machine has two options. One lens with 100 micro spot and another one with 35. So you can change the lens.
And the fitting of the lens in its place, is it adjusted by the machine? So why do you put references? This is experimental work. Why are you adding references, 4 and 10?
They did the same thing.
But you didn't say, it doesn't give any sense to put a reference. And the page after, just go down please. Yes. Go down again. Yes, stop. It starts with where kept. The third line. The flow diagram shown in figure 3.2. Figure 3.2, can we see it? It's below. Is this a flow diagram?
No, it's not a flow diagram.
Huh? It's a flow diagram. It's not a flow diagram. How did you measure the heat affected zone?
It was measured from the side of the macro channel.
Yes. How did you know it?
How did we know?
Here is the channel. Till where is the heat affected zone?
On the side of the macro channel.
Yes, I understand it's on the side. But till when? Here or here or here? How did you measure? You are giving values.
We use the microscope.
How? Here is a micro channel. It's open here. How did you know that the heat affected zone is still here?
Yeah. But
Nothing is stick to you.
There's a change in color of the should clarify. هو طبعا القصه دي بتاعت كذا مره فهو يعني حاجات تخيل انها مره بس
يعني هي محطوطة كأنه حضرتك هو بيقيس المسافة من هنا لهنا يبقى هو كده. ليه؟ And I think you should have done what we call a heat balance equation for this process. You have a power input and a power output. Part of this power is for removing the material. Part is conducted through the specimen, and part is reflected and radiated. You should have done this. And then I have one more question. Sorry, Yanni, but you gave me a long time to revise the thesis, so I had to read it all. This is the problem. In page 57, 624. Yes, this equation. In this equation, W equal 162.5. You have equation. You have P metallic and P non-metallic. What is the difference?
you say? I don't hear.
You have P in italics and P was not in italics. What is the difference?
No, there's no difference. They're the same.
Okay, you should correct all this.
There's a list of symbols.
ده كلها كده. واحد italic واحد مش italic.
By the way, all of them should be italic. If a symbol should be italic, then you correct it.
You should correct it in all the systems. But then I would prefer to see cross sections of the microchannel. You have shown one only something like this. But يعني الشيب بتاع المايكروchannel.
Cross section. هو عرض واحد.
هو عمل واحد كده بس I think it's not clear يعني. I think so يعني.
هو في بس
هو عرض واحد مش عارف الفكرة.
يعني عايز اضافه فيه يعمل بس
يعني يبقى باين الكروس سكشن والكونستي. لان هو مطلع يعني كذا شكل يبقى يعني لو باينين يبقى احسن.
حضرتك عايز في كل تجربه يعمل
لا مره بس يشرحوا يعني والكيرفز.
هو موجود واحد بالفعل. هو موجود واحد الكروس سكشن بتاع البيت شيب ده كان اكتر في واحد. هو طبعا اتمنى ان مع كل تجربه ان هو عمل 20 تجربه 3 تجارب نعملها بالاسرع. بس طبعا ده بياخد بروسيس طويله جدا في السي دي ليزر مايكروسكوبي سلايد. فهو بياخد عينه عشان يقدر يكونكلود بس
You have used coating by aluminium and then you removed it. And you made the opening while the coating was present.
Yes.
Right. In this point, you should have spoken about what is known by the etch factor. You heard what is the etch factor? If I have a part like this, here is the coating. The part will not be etched from the beginning as you have shown us. There is something called the etch factor. You should have included in your thesis. في الاتشنج سبارت في الاتشنج. نعم ايوه بس في كوتنج. ايش عرفنا ان نخليها ما تعملش الهيت بتاع الليل ما اعرفش.
بس خلينا اوضح بس او استفهم حضرتك. احنا عملنا وعملنا اتشنج.
ايوه
عملنا اتشنج
اتشنج
وكنا كله الالومنيوم ده شال كله.
بعد ولا قبل؟
لا بعد. احنا عملنا حطينا الومنيوم حفرنا وبعدين شلنا الالومنيوم.
ايوه ما ده اللي انا بتكلم عليه. يعني هو ادي الدور بتاعه عمله كده وهنا كان في كوتش صح؟ فالليزر كان شغال. في هنا حاجه بقى اسمها الاتش فاكتور ده ممكن يدخل جوه.
الليزر ولا الالومنيوم؟
لا حته الاتش.
الاتشنج ياكل في التلت ده، ياكل التلت ده يعني حط صوت كده. الاتشنج ده
ايوه بعد الماشين
وهو الومنيوم اتشن بياكل الالومنيوم بس مفيش حاجه تاني. مفيش حاجه تاني. يعني هو سيلكتيف. هو سيلكتيف اسمه الومنيوم اتشن ترتيبه كده الالومنيوم بس. يعني حتى في المايكرو ماشينينج حتى في بنعمل اتشنج بالمناسبه في الموبايل في المايكرو الكترونكس بنعمل اتشنج لماتيريال فيري سيلكتيف وما ياكلش اللي جنبيه.
اوكي. Many thanks, Joe.
احنا بس طبعا بشكر الدكتور سامي على المراجعه الدقيقه جدا دي. انا متهيألي يعني اشد من الكمبيوتر نفسه. شكرا جدا. ان شاء الله.
No matter of fact, Dr. Samy covered all the aspects of the thesis. I have some comments. Chapters 3 and 4, 5. Long titles. Why? Everyone's three lines. The introduction. The introduction. You have mentioned 40 references, 51 references. There's so much in the introduction. It's not a reflection review. You should minimize it. But now, please accept.
You have many.
And if you mention some reference in the introduction, you should mention the name of the author and the year of publication. Not the number. Here you mention the number only. The introduction is different. Why you don't make a flow chart to submit the sequence of your thesis? You missed this.
I will die.
Also, by the way, sometimes if you mention few papers or few researchers, and sometimes you say few, you know the difference between a few and few?
Sometimes I did what?
Or is it something right without thinking?
I don't understand the question.
Search about it. There's a big difference between few and the little and greater.
English.
Chapter 2. I have mentioned the carbon dioxide laser. What about the other techniques of non-traditional machining to make the microchannel? You have not mentioned anything about the other techniques, like electrobeam machining, abrasive water jet machining, water jet machining. You have nothing about this. Doesn't mention anything about these methods. Just carbon dioxide laser. You don't agree with me that the aspect ratio could be replaced by the curve geometry?
That is possible.
Aspect ratio in this work
It's possible.
is the two experimental data divided. But curve geometry was better to measure it as a slope or constant of the shape. He made the gold and in Borg. Yes, another thing. What do you mean by high surface thickness? Borg or rough surface, fine surface?
Like just the professor.
You mentioned in all the paper and the work, high surface roughness, low surface roughness. Should define high surface roughness is poor or rough, and low surface roughness fine. You get me confused. All the reading, I am confused. What do you mean? Rough or fine? This is a straight. Mention something. It's not clear. You have mentioned in page 15, last reference 26. However, the reference on the figure 26. What is the right?
Section.
26? 15.
What is the section?
15. 26 or 27 is the reference.
I mean, under which section?
Under which section?
261.
261. 261. Page 14, 15. 26 and here 27.
The figures?
Yes.
Mm.
Review it.
Yeah. Reference 44.
44?
Coming from up. What is
27. 27. Cross section of Samy. It's the cross section. Yes. What's the meaning of aspect ratio? What do you mean by aspect ratio?
Aspect ratio?
Yeah.
The meaning?
Yes. It is a ratio. It is the same in the conventional machining or not? Yeah. يفتح ويقسم الماشين. لا حضرتك مختلف عنه. Yes, in page number 20, you are talking about artificial intelligence.
And a section?
22.7.
This one?
Yeah.
Okay.
Artificial intelligence modeling of carbon dioxide gas. And we have put figure 17. This figure not belong to artificial intelligence. It belongs to 7 quality control tools. Not artificial intelligence. You know the name of this figure?
Yes, 2.17.
Yes. What is the name of this distribution or this diagram?
It shows the parameters of laser micromachining.
Yes. What do you call it?
I put it here because I was introducing the parameters here before.
This fishbowl diagram.
Okay.
Ishikawa diagram. Cause and effect diagram.
Okay.
Not artificial intelligence. Chapter 3 is about the experimental work. You should clarify what is the number of the samples and the experiment. 72 divided 36 and 36 on 24 samples. You need me to, you have to be precise in mention the number of experiments and the number of the samples. Replication.
Do you consider replications?
No, the replication was under the response surface methodology, chapter 4.
Chapter 4, experimental investigation of carbon dioxide laser. Yes, using response surface methodology. Great. Page 34. You have mentioned that the number of experiments is 18. What is your source for this number?
No, the 18 was when we were designing in the software, but we replicated 3 times, so we conducted 54.
According to you,
I was describing the design in the software when I mentioned 18. Then I added that we repeated 3 times.
according to your assumptions, you have used CCD, Center Composite Design. If you use the CCD, it should be 20 experiments, not 18.
20?
If you use Benkel, you know Benkel? The number of experiments will be 15.
How do we get 20 from CCD?
It is already available. 3 level or 3 factors in CCD, 20 experiments, and in Benkel, 15 experiments.
We had 8 experiments representing the factorial points, and then 6 for the actual points, and then 4 for the center points.
Yes.
That's how we got the 18.
Yes. You have measured. You should classify it. Factorial, axial, and center point.
Okay.
You have no right to reduce the number of points. You have assumed that alpha equal 1. Why? Alpha is assumption. What should be calculated? Why you consider each one equal 1?
We borrowed from the references. The work done before.
What is the case that alpha equal 1? Only case. Unit? If it is cube, only. Not a general case. Alpha should consider or calculate from root mean square of the number of variables. I agree with Professor Samy. There is no any graph for the microstructure. You know that for polymers, you call it sometimes configuration, not microstructure. You know how they measure it in the metals? The heat affected zone.
In the metals?
How they measure the heat affected zone in metals?
In metals.
Yeah.
We measure in polymers.
No, I know, but I ask you.
That one I'll check about it.
What's the maximum surface roughness you have got from your work? Surface roughness in page 43 reached about 300 micron. Yes.
10. 310.
Okay.
310 for the uncoated.
But here in figure 6, chapter 6, H.
What was the verbs?
Chapter 6, figure 6, page 43.
The roughness. What
Figure
was,
6.
what was the full depth?
56. This one?
Yes. Sure. 300.
And 10.
Huh? So much.
Well, they uncoated. It was not coated.
Even have you could, you can consider it surface of it's out of surface.
Check the figure. What was the full depth?
That's 998. Well, they uncoated.
What is the shape of the microfluid?
It's supposed to be
It
rectangular.
is rectangular.
What we consider.
How you can consider?
No.
It is considered or measured. What about the V shape?
This is what we call
V shape or rectangular? V shape or rectangular?
This is the shape.
V shape. But he mentioned that we need a rectangular microchip. Right?
يعني explains this. Normally, microfabrication is traditional microfabrication, which is very expensive. So you get rectangular cross section. But the rectangular cross section does not give function. You need just a group to follow the
I'm talking about You know what? The factors affecting in heat affected zone? The factors? What are the factors affecting heat affected zone?
One of them is power, the laser power. And the scanning speed and the fast mode. And also the nature of the material.
And what about the material itself?
The nature of the material is.
What factor is the material affecting in heat affected zone?
I think the melting point.
Melting. What about the thermal diffusivity?
As well. And the thermal conductivity also.
all thermal properties of the material.
It's careful. Yes. Yes, figure 18 in chapter 6. You have repeated it many times. Why?
Figure 18.
Figure 18, chapter 6.
Figure 18.
Yes.
Or 6 point something.
65.
6.5.
The number of the page, 65.
No, the figure. Now the figure.
Yeah. Figure 18.
618.
You have repeated this figure many times. The same figure. Why? $18, 23, 28, 33, 38. The same figure. So it has been repeated every time. What?
This one?
No,
They are different.
Not this is
This is 618.
the AMS in FIS model. I've repeated it many times.
This is 618. They look the same, but they are not the same. This one?
No. Figure 18, the structure of the NFIS model, AMPIS model of microchannel widths.
This one.
Ah.
It is not repeated. They are different. They look similar.
Different about widths and depths. And
Because when we were doing the AMPHIS, we consider one output at a time. That's why we have different figures for the different outputs. Yeah. AMPHIS does not consider all the outputs, only one. We loaded all the inputs and one output at a time to get. So we have 5 of this for the 5 outputs.
yes, every factor you make
Yeah, one at a time.
I don't need to put it. Another method.
So what should I put? Should I put for only one?
I think you have put it 5 times.
Because there are 5 outputs.
It is different in each case,
Yeah. Because the values are different.
but the same technique.
So what should I do?
Just refer to the first one.
Okay.
Avoid the repetition.
Okay.
خلاص. لا. I finally I'm talking about the conclusion. New results you have mentioned for every chapter the percentage or improving or disimproving. But when you are talking about the conclusion, you miss this point.
I will add.
You make it more generalized.
Yes.
The conclusion is not condensed. I think you lost your effort in this conclusion. Why?
But this
It should be
happens.
condensed,
This happens in the process of learning. Right? We learn, we go.
not general.
Sure.
And the first chapter of the conclusion is more general. Doesn't belong even the thesis itself.
We'll adjust.
Yes, another point. During your results and discussion, you have mentioned 5 new references. Why? If it is important, why you don't put in the first, the experimental, theoretical, introduction, and literature review? There is no new references in the results and discussion. You should mention before.
Okay.
Results and discussion talking about your results, not the others. So I think it was better to mention it before.
Okay.
And you can write, I agree with X, I agree with Y, and so on. Yeah. Not to mention it in the results.
Okay.
I agree with Dr. Samy that your Arabic language is not good.
It's 0.
Yes, 0.
Actually, the translation was done by Professor El-Hofy.
Yes, I know. Thank you.
Thank you very much.
Ahmed. Yeah, thank you so much. حبيبي.
Dio media.
Go, yeah.
It's supposed to be done after celebration.
After presenting the work and successfully answering the examiner's questions, the committee recommends granting the student, Job Lazarus Okello, the MSc degree in Industrial Engineering and Systems Management. Congratulations.
Put this on my head. Put that one. The cap? It's supposed to be.
This way. Yes.
Habib, oh, you heard that? Huh? Yes, you. Making full coverage.
We wore the crown.
We did it.
We did it.
We did it.
We wore the crown. After carrying the cross. Shall go past who don't have You're capturing it? Good. We wore the crown, That's a job, congratulations. Shukran, shukran. Okay.
Okay. Take a photo like that. That's a video. Soko taller than you put again. Is it a video or photo? Video. Video.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Everything I do so instinctive and so passionate. Every word I move so descriptive like an adjective. I got a vendetta against people who patented being negative when you should be getting after it. I got facts over tracks, this and that. Spitting slow, spitting fast, I could roast, I could gas. Think I'm okay at last, but I don't know if that can erase all the past. And the pettiness, a reflection of the emptiness. Hilarious, you think you're worth my time, you're delirious. Mysterious, because you hide behind a fake exterior. Inferior, you know I'll always be a bit superior. Get off of me, this ain't no humble brag. I want you to hear words, you can say them back. I want you to feel free from the chains at last, and to believe in what you got, it was built to last, yeah. Now that I've been put through hell, I never got anyone's help. I had to do it all myself.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Gonna learn the consequence of being incompetent. Mental health is confidence, dreams into modestness. I'm not here to save the day, that's for you to take away. I could play a million mind games, but instead I say something not illogical, something that is topical. Rub it on and watch it go, make yourself unstoppable. Dreams are irresponsible, but they're always possible. If you just believe, you could be so remarkable.
Thoughts in my head, a collage and they spread. I'll be great one day, going off of my meds. No, I'm not giving up, no, I'm not giving in. I will make it to the top, taking off in the wind. I gotta make it, I'm saving every day to taste it. I'm patient, but my mind, it can hardly take it. I'm chasing a dream that I've had for several ages. A vacant, modern kingdom for the taking.
Now that I've been put through hell, I never got anyone's help. I had to do it all myself.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up.